The problem with bonds is we have no simple way of determining what phi is. R, unlike S, is not a tradable security. We have the advantage when we're dealing with stocks that S is a tradable security, and therefore we can identify simple contracts on S that satisfy the differential equation. And as soon as we do that, we can determine what phi is. We can determine what the risk, what the Sharpe ratio is. And indeed, that Sharpe ratio is determined by the parameters in the S stochastic process. When it comes to bonds, we just have no way of identifying how the market is pricing risk. We have no way of identifying phi, the Sharpe ratio. We know it's the same for every bond, but we have no way of observing it because R does not trade. We cannot write down any simple derivative security on R that we know must satisfy the equation that would then give us the necessary insight of what phi is. So for interest rates, being not tradable, the DR process really doesn't tell us anything about how the market is pricing risk. The market's not trading R. It's trading derivative securities on R. And so in order to price bonds and to price derivatives on bonds, we have to make an assumption about the Sharpe ratio. We have to make an assumption about the market price of risk. It's not observable as it was for stocks, and it will always be a free parameter in our modeling. But once we observe it, or once we make an assumption about what this Sharpe ratio is, it'll be the same for all securities. We know that for sure. But in the differential equation for bonds, we're stuck with that phi, and we have to make an assumption about what it is. It does not come from the process DR, the DR process. So we have a PDE, a partial differential equation, that characterizes claims, any claim that's a function of interest rates. A simple zero-coupon bond is, in fact, a derivative security on R. It's a security whose value derives from the value of R. So a simple zero is a derivative contract. We can also then think about more complicated derivative contracts on R, various types of options. So now what we're going to do is create a risk-neutral process. And the typical procedure is we're going to subtract the risk premium from the drift. You recall that's how we create a risk-neutral process, is we take the drift of the original variable and we subtract its risk premium. Well, what's the risk premium? It's the numerator of the Sharpe ratio. So if I multiply sigma times the Sharpe ratio, I get the risk premium. We recall the definition of the Sharpe ratio. It's the risk premium divided by sigma. And I know what sigma is. So the risk premium is just the Sharpe ratio. So Sharpe ratio times sigma. So this is now going to be a risk-neutral process. As usual, there's a little bit of a trick here. This is technically a different DZ than I started with, because the only legitimate way I can subtract this drift term here is I need to move it into the DZ term and then use Gersonov's theorem that says I can change the probabilities there, and by changing the probabilities I get back to an original Brownian motion. Okay, so there's a little bit there are a few steps here that we've consolidated. We are not allowed to simply change the drift. We started with a process for R, and what we do is we change the drift by moving a canceling term into DZ, and then what we want is that new DZ to again be Brownian motion. Well, it has a drift in it, and the only way I can get rid of that drift is I have to change the normal distribution that determines the Brownian motion. We saw this before in the case of stock. It's the same idea. It turns out that once you have a risk-neutral process, and notice again that that risk-neutral process still requires you to know phi. Can't get away from that. You have to make an assumption about phi to create the risk-neutral process for R. You can start with any process you want for R. If you want it to be a risk-neutral process, which we need to price bonds and options, we need an assumption about phi.